Hey guys, welcome to the first video on substitution and elimination reactions. So this is going to be an intro video into these types of reactions, and in the later ones we're going to get into the more detailed stuff. Now this is a topic many people consider to be much more difficult than what you guys have done in terms of reactions already, like comparing alkene reactions to this, and a lot of people struggle with it. Okay, so this is it's a very important topic. It's probably going to cover the majority of your exam 3 material, right? So you got to learn this stuff really well. All right, and so we're going to have a large amount of videos for these and a very large problem set. I think I'm working on it now. I have like 40 something questions already in there. All right, so you'll have a lot. So this is just going to cover an intro into what the kinds of reactions are, and later we'll go into how to decide when one of them is going to happen over the other, with a lot of examples, of course. All right, so let's get into it. So there are 4 types of reactions when we're talking about substitution and elimination reactions. There's SN1, SN2, E1, E2. Okay, the S means substitution, and the E means elimination. All right, the N for those SN1 and SN2 just means nucleophilic. All right, don't focus too much on that. What the numbers mean is they talk about the rate law. So yeah, it's thinking back to Gen Chem again. So all it is just rate equals some constant K, doesn't matter, times your substrate. That's for anything with a 1 on it. So SN1 or E1, and that's considered first order kinetics. The other one is for if you have a 2 in front, you're going to have K, substrate, times a nucleophile, or a base. And that's second order. Now, there is a reason I'm bringing this up. A theory question very often comes up on exam 3 or on the final, referring to the rate law. Okay, at the very least, have it on your index card, but please know it. Okay, they will hint telling you this reaction follows first order kinetics, so that should automatically narrow it down to SN1 or E1. And how we tell if it's first or second order is you just look at the exponent. There's only 1 there, so it's first order, whereas here we have 1, 2, so add them up, you get 2, second order. All right, so please know that. So all that means is for first order, the rate is entirely dependent on the substrate, which is like our original starting compound. For the SN2 and E2 reactions, it means that the rate is dependent on both the substrate concentration as well as whatever we're using as a nucleophile or base. Okay, so I will be referring to these ideas as these videos go on. All right, so what we're going to do is we're going to just go through a quick overview of each of these 4 reactions, and we'll get more in depth in the future videos. So first, SN1. All right, S means substitution, N means nucleophilic, and the 1 again means first order kinetics. Another way you could see first order written as is unimolecular. And then if you had a 2, it would have been bimolecular. All right, again, just something to know. Okay, so I'm going to show you guys what a general SN1 mechanism looks like. Okay, so I have this carbon compound with a chlorine, right? All of these reactions, SN1, SN2, E1, E2, require something called a leaving group. Okay, this is a leaving group. I'm going to, in the future, just abbreviate this as LG. All right, just keep that in mind. And so I'm going to react this with something like H3COH, which is just a methyl to an alcohol, so methanol. You could see it written like this. Right, you've seen these before. All right, so anything with the 1 in front, SN1 or E1, they follow a carbocation mechanism. Okay, What that means is the very first arrow is the leaving group leaving. So the bond between the Cl, or whatever your leaving group is, and the carbon must go to the chlorine. And knowing stuff that from what you've already learned, we get a carbocation. And our chlorine is just floating around. Okay, this is very important. SN1 and E1 have the same first step. They must form a carbocation. Okay? If you're not forming carbocation when you're doing an SN1 and E1, you're doing it wrong. Okay? So this is a very important thing to understand. And also, the formation of the carbocation is called the rate determining step, also called a slow step. That's just because that determines the rate. Okay? So we see our leaving group leaving and we form a carbocation. Then we're going to react it with our solvent or our whatever we have here, so CH3OH. That comes in. We're going to get this structure CH3H plus, and all we do is deprotonate the H, and you could just either draw an arrow like this, or if you want to be a little bit more proper and show something grabbing it, I'll just write another CH3OH, and then we get OCH3. Okay, so let's evaluate what we just saw. We started with a carbon compound, right, or just some sort of alkyl group with a chlorine. All right, the chlorine is your leaving group. It is not always chlorine. I will show you guys the other stuff that you can have as a leaving group. The very first step is the carbocation formation. Then CH3OH, or our solvent, usually this is a solvent, attacks the carbocation, and we just deprotonate afterwards. All right, and so you can see the chlorine was swapped out for OCH3. Okay, so the key points here is we have a carbocation intermediate. We have the carbocation formation is called the rate determining step, and here the solvent is often the nucleophile. So remember, nucleophiles are things that attack. All right, in this case, our CH3OH is what attacked, and it's also acting as a solvent. Okay. Now the thing here is, you have to see that the leaving group must leave first. The solvent cannot just attack outright. The leaving group must leave first, and then it can attack. All right, and we'll go more why this happens later on. Now you can see that we have a carbocation. So if you have a carbocation and you can form a more stable carbocation through a shift, that happens here also. So that means shifting, carbocation shifts possible. Okay. Now they bring stereochemistry into these questions. So here, if we were given this compound reacting with here we have a Br, and that methyl right there, and we reacted with H2O. Okay. So our first step again is going to be the Br leaving, and so we get a carbocation. Now remember, an sp2 carbon is planar, so that means when the Br leaves, right, that dashed methyl will be now planar. So I'm going to just erase this. I'm going to redraw it here. So now we're going to have a methyl with a carbocation, and now the H2O can attack, and it can attack from either the front or it can attack from the back. So you're going to attack this way or kind of from the back. I know it's flat, so it's obviously not easy to see what I'm trying to show coming from the back. But what I'm showing you here is that similar to when you syn and anti stuff with carbocations, we can get two products here, right? So, you know, the OH is going to be like this now. Sorry, the H2O plus, and the methyl here was dashed. So when we have to deprotonate this, and we'll get an OH. So you can see we can add the OH either wedged, or we could have just added them dashed, which means that the methyl is wedged. Oh boy, wedged. Okay, so we have retention because our BR was wedged, and inversion. Right, so we can get a mixture here, 50-50. All right, so just always watch that out. Well, watch out for that. Okay. So now we're gonna go to we're gonna go to E1. Okay. E1. So what would this mechanism look like? So we saw the substitution reactions substitute. So what about an elimination reactions? Br. All right, and here reacting with H2O. So elimination reactions, they take a hydrogen, right, and a proton, and the electrons from that hydrogen carbon bond collapse onto our compound to kick off the leaving group. Okay, so we form a double bond. All right, and so remember that 1 also means unimolecular. All right, just gonna keep bringing that up so that you guys can remember it. Okay, so we need to take a hydrogen to kick off our leaving group. In this case, I drew Br, right? So again, like I said, I'll have a video talking about the leaving groups, all right? But I do want to just talk about the mechanism, okay? Similar to how SN1 happened, right? We formed a carbocation. The same thing must happen here. First step is the Br getting kicked out. And we get this carbocation and the Br minus. And remember we have a hydrogen here. Okay? Then our H2O is going to attack that hydrogen. And the bonds in that dashed hydrogen carbon bond are going to collapse down to fulfill the octet of that carbon, that carbocation. We now get this. And remember, no bonds off of carbons with double bonds have stereochem. So that that wedged methyl is now going to be planar. All right? And so you can see that we have a carbocation intermediate, right? Our leaving group leaves first. Shifting is possible because we have the carbocation intermediate. But now instead of attacking the carbocation, we grab the H and collapse the bond downward to form a double bond. Okay? And so that's an E1 reaction. Okay? So now I'm going to talk about SN2. And these are just bare bones in terms of how I'm showing you guys this. Of course, we will get into more detail. I just want you guys to be a little bit familiar with it for the next videos. So SN2. Now we're getting into the category with the numbers 2. So we have this substrate here, this is Br, and we're going to react it with NaCN over DMSO. Okay? So let's look at what we got here. SN2, the S means substitution, the N means nucleophilic. All that means is something is attacking, right? And the 2 means a bimolecular. Okay, just remember that, bimolecular. All right? So we have this compound, NaCN. All right, now you have to understand, Na, or anything really in the first column, right, is of the periodic table. The first group is will dissociate to a charge of +1. You get a plus here. That means that this had to have been a minus charge. And remember, sodium doesn't really do anything, so we can just kind of ignore the sodium and focus exclusively on this Cn minus. That's what's really happening here. Okay. What I have underneath here, that's called the solvent, and this is something called a polar aprotic solvent. Polar aprotic. Now, do not focus on this right now. I just wanted to say the name. Do not do not look at the solvent right now. Okay, it's just going to be more confusing. Just focus on the reaction mechanisms. Okay, we'll get into all this stuff later. This is a topic that is very confusing initially, and it's best to watch, I'd say, all the videos through before actually starting attempting full-blown practice problems. So we saw that in the SN1 and E1 reactions, we formed a carbocation, right? It happened in 2 steps. You had to form the carbocation first, then we either had substitution reaction or the elimination reaction. In SN2 and E2, we do everything in 1 step. So instead of waiting for this Br to leave and we get a carbocation, instead what's going to happen is this Cn minus is going to directly attack that carbon with a Br and force it out. Okay? And so we would put the Cn in place of the Br. Now, the thing to watch out about SN2 is SN2 is called a backside attack. So this Br is wedged. So if you hold up a pen right now, you try to show what a wedged Br will look like, you would point the pen to you. So the nucleophile, the thing that is doing the attacking, will come in from the opposite side. So it's almost coming in dashed. So that's the whole thing about the stereochemistry with regards to SN2. If you have if your leaving group is on a chiral carbon and it has stereochemistry, SN2 always results in inversion, always. So because this Br is on a chiral carbon and it's wedged, we are going to draw our Cn dashed, right? And also, if you're wondering on Oscar how you would draw this, you would have a carbon triple bonded to a nitrogen. That's what a Cn group looks like. Okay? And so that's how an SN2 mechanism would work. All right? So always keep in mind, it's a backside attack, so inversion of stereochemistry. There is no carbocation intermediate, right? So before we had carbocation intermediates, which means that they can shift. These do not, SN2 and E2 do not shift, okay? So again, yeah, keep that stuff in mind. So that's an SN2. And now let's go to the last one, E2. All right? So what would the E2 look like? So let's draw this example. Ethyl, our leaving group, and the H, and a hydrogen here. And I'm going to react it with NaOCH3. Now remember what I said about Na, right? Remember, it becomes a plus charge, and we can basically ignore it. This OCH3 minus, this OCH3 gets a negative. So we just exclusively really focus on that. Moving that over. Okay? So now remember, the 2 means it's bimolecular. And elimination reactions grab the hydrogen, right, to kick off our leaving group. Now in E1, we saw that the leaving group left and formed the carbocation, and then the H was taken to form the double bond. In this case, similar to how SN2 is different from SN1, this happens all in 1 step. Okay, we call that concerted. So in this case, this OCH3 is going to grab the H. The bond is going to collapse downwards and kick off the Br in 1 step. Now I'm actually going to slightly change this compound around. Instead, I'm going to make the methyl dashed and the hydrogen wedged. Okay, so now we know that's going to happen in 1 step. So we have to show the OCH3 minus grabbing a hydrogen. Now, the very important rule in E2 is that the hydrogen that you are grabbing and the leaving group that it is kicking off must be opposite stereochemistry. So if your Br is dashed and your hydrogen is wedged, that works, right? And remember, we look at the hydrogens on adjacent carbons, not if you had a hydrogen on like this carbon or something. We wouldn't be looking at that because our leaving group is there. If your Br was dashed and your hydrogen was dashed, you cannot take that hydrogen to kick the Br out. They must be opposite. So sometimes bond rotations play a role in this. It's on your workshop, so definitely think of that. All right, that rule cannot be broken. So how would we show this? O would grab this H, and we see that the H and B are opposite stereochemistry. This bond collapses down and kicks off our bromine. So we form a double bond there. We had a methyl right there, right? And remember, because they're on double bonds, they are planar, okay? So that is going to be an E2 reaction, right? Now, one quick thing about E2, I formed the Morse substituted double bond, okay? You can see that that is the Morse substituted double bond. If I had now this structure, right, where the H's and the Br are the same stereochemistry, now, like I said before, we can't break that rule of the Br and H not being anti. They must be anti. So even though form the more substituted double bond would be here, and that's more stable, sorry, you're out of luck. So what we would do now is go to the hydrogens to the left, because we know that one of them would be wedged, one would be dashed. So the OCH3 minus would actually grab one of these to collapse downward and kick out the Br. And remember, it would grab the wedged one. So in this case, our product would really look like this. And with that dashed hydrogen. Okay? So when we talk about the major and minor product, right, you must kind of watch out for this sort of anti-relationship, right? It is very important. Otherwise, you're going to have issues, okay? So in the above example, we are going to get this one because our BRs are anti. Here we can't grab this Br and H together. We have to pick the other Br and H. Okay, so that's an E2 reaction. So that's pretty much sums up the general idea of these two. All right, we just want to get the bare idea here in terms of the mechanism, and we're going to go a little bit more in depth in the later videos. All right, so if something here didn't make sense, please feel free to email me, go to the CLC, talk to the TAs, they're really helpful. And yeah, I will see you guys in the next video.